Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on entire device simulation for electromagnetic compatibility. Before we start the presentation, let's review the user interface. On the top of your screen, you will see a bar with 4 options for you to click. To ask questions, please click and open the Show Conversation option. This will show the meeting chat, and this is where you may ask any questions you have during the presentation. At any time during the presentation, you can submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Now on to today's speaker. Tim McDonald is president of Electromagnetic Applications, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time, with more accuracy, and at a lower cost. He is a consultant to NASA DoD major primes for specialty engineering of critical systems, development of novel material solutions to EMC problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Without further delay, I will pass it off to Tim to get us started.
Thank you very much. So let's talk about the design workflow for electronics. So typically we design the device and eventually prepare a prototype. And that prototype, at some point, the entire device will go into an EMC chamber for EMC pass-fail testing. That is very late in the product development life cycle. Failing a test at that point can be very painful. So what we recommend in best practices is during that early design phase, we introduce an EMC simulation phase where we have the ability to make mitigations at a time when production has not ramped up. And it's cheaper and more practical to make changes. So it's about moving things further to the left. The product we have been talking about today is Ansys EMA3D Cable. This product is available through Ansys and its channel partners. It's a device or unit level electromagnetic modeling solution. It has the ability to import the CAD, prepare the mesh, run the simulation, and analyze the results all within the product. You'll never have to leave the user interface of EMA3D Cable. So we can use EMA3D Cable for pre-compliance analysis. We can look at individual components of our device, and we can predict the full device EMC performance. We can predict how it will perform in the chamber. And finally, we can also do full platform tests. So if the electronics are, say, installed in a vehicle, then we have the ability to consider the vehicle and structures in a cost-effective way. So the whole goal here is to get away from the build test paradigm and now add a phase where we do prediction earlier in our program. It's much less costly to make changes early in your program, and you're going to take less risk into that testing phase. So we're going to talk about some of the individual EMC environments next. We're going to go through them one by one. We will talk about radiated immunity, radiated emissions, electrostatic discharge, conducted emissions, conducted immunity, signal integrity, power integrity, and finally, transfer impedance. Okay, the motivation here. So there have been on the market really great tools for simulating printed circuit board emissions. For example, Ansys SIwave, Ansys HFSS, best-in-class tools for PCB emissions. But those emissions are heavily impacted by cables and enclosures. So when we do EMC testing, we're not testing PCBs levitating in a vacuum. Those PCBs are installed in real enclosures, and those enclosures have cables in the enclosures. There's cables outside the enclosure. The cables penetrating through the enclosure affect the emissions. The shields and termination of the cable have a big effect on EMC performance. There's holes in enclosures. They're never perfect boxes. There's always holes, imperfections at the leads. There's seams and joints. We may have complex materials like EMI absorbing tapes, cable chokes. Existing methods for simulating the full electronic device can be time-consuming to build the model. That's where we fit in. EMA3D Cable is for the complex enclosures and cables. Um, what are distinguishing features? EMA3D cable's got decades of validation heritage. So it's been used for EMI, EMC since the 1980s. It's been developed specifically for EMC and related environments. It is a full wave solution of the electromagnetic equation, so it's applicable to a wide class of problems. EMA3D co-simulates that full wave solver with a cable wire transmission line solver. So it's actually a modification of traditional transmission line theory, but that allows us to model complex 3D geometry self-consistently with complex harnesses in a computationally efficient way. As mentioned in the promotional video, EMA3D cable is easy to use. It's reasonably easy for new users to pick up. Expert users can really handle complex CAD with the shortest period of time. And again, we're integrated closely with Ansys SIwave and Ansys HFSS, so we can pull in PCB and antenna fields. Okay, first, let's talk about electrostatic discharge. We're first going to consider a case where the ESD is forced to flow on a cable. So designers want to verify that their performance of their device are going to survive the ESD testing. So the ESD may couple onto cables directly or may couple through fields and waves. Generally, we need full wave analysis so that we're solving Maxwell's equations. And ESD is better posed as a transient problem. The problem is the enclosures, the cables can be incredibly complex, multiple layers of shielding, complex 3D geometry for the cables and the enclosure. EMA3D addresses those concerns by giving us the ability to provide the transmission line solver for the cables self-consistently with the 3D solver for the structures. The workflow is rapid and relies on the mechanical CAD with very limited requirements to clean or prepare for simulation. And we can predict the stress on electronics without the need for frequency sweeps or other types of post-processing. So this allows us to move our ESD analysis to the left in our program. We can know with confidence whether our unit is going to pass ESD testing before we create a physical prototype. So that can shorten our development schedule and decrease churn and complex late phase design changes. So in this case, we're going to talk about ESD to a monitor. The monitor is connected to a cable. The cable is connected to a computer, and the computer is the ground point. There's no grounding assumed in this case at the monitor. So that means all the current is going to have to flow on the data cable. So we're applying a standard ESD waveform. And in this case, we show how that current flows. You can see it flows onto the monitor and then flows through the cable to the computer itself. So the only path for the current to flow to ground is through the cable. So EMA3D cable gives us the chance to very quickly interactively change the design of the cable. We can add a pigtail. We can switch that to a 360-degree connector termination. We can change details of the braid. We can change from a foil to a weaved cable, or we can have both. We can change the weave angle and very quickly see the results of that change. In this case, we can add an extra layer of shielding and we can very quickly see the results. And also we can feel confident that we're getting the right answer. In this case, my colleague, Dr. Kitagorski, is showing a validation where she's applying a transient pulse onto a cable shield and at the same time is measuring through an oscilloscope the induced voltage on the inner pin of that cable. And we take as well the current flowing on the overall cable itself, and then we apply that measured current to our simulation. So that's the reason that the simulation is noisy, because it's based on the measured outer current. The simulation is determining the coupling to the inner pin, and you can see we have great overlay between the scope measurement and the simulation. So we can trust that we're getting accurate results for this case. Okay, we've talked about ESD. Let's move next to the radiated emissions environment. So this is a very critical requirement. In fact, maybe this is one of the easiest EMC standards to fail, radiated emissions testing. Um, I think most companies that have to do radiated emissions analysis would like to be able to predict this. Again, the challenges here is our units are complex. We've got PCBs, cables, grounding and bonding of things in that enclosure. The enclosure itself may be complex. There's cables inside the enclosure, outside the enclosure. What EMA3D can do to address those concerns, we can pull in the PCB simulation from other tools and capture those fields. And then we can add the complexity of the enclosure and the cables with the least amount of analyst effort in the marketplace. So that means you're going to go from getting the mechanical CAD to getting a running simulation in the least amount of time possible. So the benefits here are we're able to predict the radiated emissions early in our program and hopefully reduce our cycle. So in this case, I'm showing a different product. This is Ansys SIwave. That's not the focus of this presentation, so I'll just mention that SIwave is a dedicated PCB and package electromagnetic simulation software. SIwave does many things, but for today, we're going to focus on using SIwave to determine radiated emissions from the PCB and package itself. So in this case, this is an example board. This is a non-proprietary Galileo board as what it's called. It's a processor, a couple of DDR memory, and we've got about 35 total nets, multiple clocks and simulated bits. So without going into the details, just know that SIwave is a very easy to use tool and can capture the radiated emissions from the board itself, capture the near fields. And we're showing just one frequency here, but this is solved in this product for multiple frequencies. We can take those field results, and it is one click in EMA3D Cable to import all those SIwave fields. Now, once we got the fields in EMA3D Cable, we've got the mechanical CAD. Because EMA3D Cable uses a voxel style mesh, it is extremely fast and easy to mesh from that mechanical CAD with the least amount of simplification. So we drop in one PCB, we can drop in 12 PCBs. We can put all of the cards from this device into the model. And we can add cables. We can specify seams using seam impedance, which is an intrinsic characterization of the seam. It makes it easier than trying to geometrically resolve a seam that may be microns. So that's another way the tool helps save time. Everything in the workflow is about reducing the time from importing the CAD to getting the simulation running. You can see the voxel style mesh that we use. It's very forgiving. It looks like Minecraft or maybe Legos. If you're older like me, you don't know Minecraft, but you know Legos. So the advantage of this style of mesh is that it's very forgiving. So for EMI, EMC, usually we're not trying to get 0.1 dB accuracy. Instead, we're usually satisfied with 6 dB accuracy. But what we get in return for relaxing some accuracy is an incredibly fast workflow and relaxation of the need to prepare that mesh for simulation. So you can see the emission of the PCB in the enclosure. You can see the radiated emissions. And let's look at the side view. You can see very clearly red is higher fields, yellow and green are lower fields. We can see the shielding of the box immediately looking at this. Those fields are driven by the PCB, which was modeled in SIwave. The fields get out of the box through the seam that we specified with the seam impedance paradigm, and we're predicting the fields 1 meter away. So this is the fields inside the box, 0.3 millivolts per meter, and the fields outside the box. This goes from, I'm sorry, this is 3 millivolts per meter. This goes to 0.5, 0.6 millivolts per meter. So we're decreasing by about 12 dB from inside the enclosure to outside the enclosure and some distance away from that. We can do this for other types of devices. So this is really the same problem, just different geometry, and we're adding cables. In this case, we've got a cell phone. In addition to the cell phone, we have a cable. We all have these charging cables that we like to lose and leave everywhere. Those cables have data pins. They have shields, braids, foils, multiple conductors. In this case, we're going to put signals on those cables, and that will create emission. We're also going to use SIwave to model the PCB and the cell phone. And we can, with one click, import the fields from SIwave and just translate and rotate that into position. And we apply the signals to the cables, and we're ready to simulate. And it really is that easy. The fields from the PCB create fields inside the phone. The fields get outside of the phone through the apertures that we defined. And we also have fields created by the currents flowing inside the cable. That gets outside of the cable shield through the imperfections in the braid and the connector. And then some distance away, we see the superposition of fields from both sources. So it really takes something that might have been considered impossible some time ago and makes it become practical, reasonable to simulate. Okay, let's talk more specifically about cables and signal and power integrity in cables. So often, to understand signal and power integrity in cables, we want some characterization of those cables as an S parameter characterization. So we want to understand the inductance and the capacitance of the cable so that we can move that into our circuit simulations. So EMA3D cable allows us very easily to extract the S parameters from complex cables and looking at them as a 3D representation. So you can see, we see the cross section and we see the length of the cable. Now this is simplified. This is just a straight cable, but this could easily be a curved cable, and that cable could be installed on a platform. We can see the capacitance to those metallic structures on the platform. So we get all of those 3D effects, and that manifests itself in the S parameters. We can export that as a touchstone file for use in any circuit solver and just wire it up, all of those conductors together. And then we can analyze it. We can extract from those S parameters the shielding of the cable shields. We can extract the crosstalk. So in blue, we're seeing the crosstalk from two conductors in the same shield. In the reddish orange curve, we can see the crosstalk between two conductors in a different pack. And so we can really see those effects. It's sensitive to the position of conductors, so we can click with our mouse, move the conductor's position, and rerun the simulation, and we see the change on crosstalk instantly. Okay, let's talk about subgrid meshing. There's times when we want to take our voxel mesh and we want to have a smaller mesh in some locations and a bigger mesh in other locations. So specifically radiated immunity. We want to be able to illuminate our equipment with an external antenna and make engineering judgments on whether we're going to have upset or damage in that equipment. And it's a very complex problem. And in the past, full device immunity was something thought elusive or impractical. With EMA3D cable, we make that more cost effective, time efficient, so that we can actually attack the problem. In this case, we're going to use two different size grids. We're going to stay at 0.5 millimeter near the PCB and package, and we're going to be at 1.5 millimeter everywhere else on the enclosure. So you can see in the top left, our subgrid array. And then on the bottom left, you can see what it would have been if we had to use uniform grid. So we can mix and match. In this example, we have a subgrid for the PCB, and then we can also import fields from SIwave. So we can do both. So in this case, we've got fields being created from the subgrid. We've got another device simulated SIwave capturing its fields using Huygens currents. And we see the superposition of those fields creating energy inside the box that escapes through an aperture, and we can measure that some distance away from the unit to predict radiated emissions. We can reverse the problem. We can put our source outside of the equipment, and we can see the voltages and currents induced on the PCB nets. In this case, we also have a cable attached to the equipment, and that cable provides a path for energy to couple onto the cable outside the unit, flow on the cable inside the unit, and re-radiate inside the unit. So we get the full effects of that cable penetration, and you can see how the energy couples to the inside of the unit, and we can predict then the voltage induced on one of those nets. And this can all be done based on mechanical CAD. It's a very quick approach. Okay, we mentioned before, there's times where we may have frequency dependent materials. Maybe we have cable chokes that are ferrous. Maybe we have EMI absorbing tape, and they have frequency dependent properties. We need to be able to use our time domain solution like in EMA3D. How do we add in those frequency dependent properties? Luckily, EMA3D, we have the ability to deal with frequency dependent properties, even though we're in a time domain simulation. So we've added this tool. We can import the permittivity and permeability as a curve. The real imaginary parts of each curve can be imported, and then EMA3D cable gives the ability for users to fit to those curves to prepare for simulation. Just to show an example of the accuracy, we packed the interior of this TEM cells dielectric with a magnetically lossy material. So this magnetically lossy material is not going to attenuate at low frequency. Once we get above a gigahertz, we should start to see losses. So we're going to compare HFSS on the left to EMA3D on the right. And in this case, the frequency dependent S parameter coupling from one end of the TEM cell to the other, you can see very clearly at low frequencies, no or very little attenuation. Above a gigahertz, we start to see dramatic attenuation increasing with frequency. So we're able to capture the same frequency dependent behavior from HFSS. So we can use complex materials with confidence. Okay, next let's talk about transfer impedance. Transfer impedance is a very important metric that we use to consider the shielding of connectors and cables. And so this may be something that we want to use as an intrinsic measure of the performance of a cable connector or cable shield. Or if we're a supplier of cables and connectors, we may be contractually obligated to meet a certain transfer impedance value. So again, whenever we're dealing with cables and connectors, predicting transfer impedance, we want to know what those results are before we start physically building prototypes. In this case, we're showing a Cat8 style connector. Cat8 connectors look like Cat5 or Cat6 that you might have at your desk right now. They're a little bit different though, because they have some metallization, so they get an electrical connection between the shield and the receptacle. So in this case, this just shows a picture of it. It's a little hard to see from this image, but trust me, that receptacle is partly metallized. It's an okay electrical connection. If you wiggle the connector, the resistance changes, but at DC, it's about 100 milliohms. So again, good, but not great shield connection. This is a transfer impedance measurement fixture. It's basically just a TEM cell connected to a network analyzer. And this is how we model this. So using EMA3D cable, we can use the 3D solver to mesh the geometry, and for the cable connection, we can use the M-harness transmission line solver. One of the nice things we can do is add a seam joint tool, so we can add that 100 milliohms explicitly into the solver. We have another option. If we don't want to spend the effort to resolve all details of our connectors, we have the option of using transmission line theory and specifying the transfer impedance directly. So in this case, I've got a 5 or 6 centimeter connector represented as this simple transmission line. And the magic of the coupling happens by specifying the transfer inductance. And we have the ability to specify that for cables. So you can see the results of the measurement compared to the 3D simulation, compared to the transmission line or M-harness simulation. So you can see we have great correlation between all three. So that means you have multiple options when simulating cables and connectors and transfer impedance. Okay, in the next case, we're going to talk about the ability to model to PCBs. So EMA3D cable can model not just conductive surfaces, but it can also model bodies. So in this case, we're going to model FR4 material. We could also model Rogers material between a PCB. And the goal here is to predict ESD, that couples through fields and waves. The victim PCB in this case is not as part of the circuit. So the only way that the ESD is going to couple to it is by field coupling. In this case, we've got a PCB, 2 layers, and it's sandwiched around some FR4 material. And we assign the material properties to the copper trace, and there's a shield around the PCB. So we apply the ESD waveform to the shield. And as you can see, there's apertures in the shield, and that's how we would couple to the PCB. So we prepare the computational mesh for the PCB traces. We prepare the computational mesh for the FR4 material, and then we run our simulation. And we can see as time goes on, it starts to turn red, and we're going to induce current as well as voltages on the nets of this PCB. So we're able to predict what is induced from this field and wave coupled ESD source. Okay, let's summarize some of the details we've talked about today. So EMA3D Cable is a solver that has been developed specifically for the environments of EMI and EMC. And over the last many decades, it's been validated extensively on these type of broadband coupling problems. So users can feel confident that if the problems are set up accurately, they can get the right answer compared to measurement. We've added details to post-process the data so that we get better correlation with measurements. It's very easy with other tools. You may be solving Maxwell's equations accurately, but you may get poor correlation with measurement because the post-processing is different. So EMA3D Cable includes some of those details, like adjusting the bandwidth, adjusting the aperture that we're measuring fields so that we get better correlation with measurement. It's an automated and streamlined workflow for setting up models using the space claim tool. Essentially, it is the shortest path from importing the mechanical CAD to a working EM model. Because we have the forgiving voxel mesh and the very straightforward method to specify cables, it's going to take the shortest period of time to build a complex model. Again, it's a rapid and forgiving mesh. So we have the minimal amount of time cleaning and preparing the geometry. And we've got the capability to include multiple sources. So we can have multiple cards. We can have multiple cables that are exciting the problem so that we can have the full device operation considered. So when we look at radiated emission, we know we've got all possible contributions to those emissions. And then finally, the tool is parallelized to take advantage of multiple cores on a PC or workstation, but it can also run on a cluster across multiple compute nodes, and it takes advantage of standard Ansys HFSS technology, and so that it can be accelerated to run very quickly. And in our next version coming up, here's a preview, we'll be adding a GPU solver to the collection as well, so that if your workstation or desktop has a high performance GPU, you'll be able to run fast simulations with the support of that GPU. At this, I'm going to pass back to Kaylin.
Thank you, Tim, for that informative webinar. Now let's get to the questions that we have received. How long does it take to develop a model of a full electronics enclosure?
Yeah, that's a fair question. So as I've mentioned, much of our technical approach is to decrease the man hours to get to that model. So it really depends on the complexity of the device. But in many cases, we can take the mechanical CAD, and if we're looking at a shielding effectiveness, we can do that in 1 day or 2 days. If we're looking at adding sources from SIwave, we can complete that model preparation in a week. But we're really taking things that might be considered a research project or might take months to do and validate, and compressing them to something that can be done in days or weeks. So it becomes part of our working process in electromagnetics rather than an infrequent research project.
All right. How much complexity of the device is required to get good correlation with measurements?
That's another great question. So, um, really, we can take a multiple fidelity approach with our simulations. If we're assessing only part of the problem, if we're worried just about a noisy cable, we can include the mechanical CAD and all of the other geometry very quickly, and we can focus on the signals and the details of that potentially noisy cable. In cases where we want to consider multiple sources, we may be able to omit the full PCB simulation and just include simplified versions where we look at the longest traces, the highest current traces, the peak DIDT, and make some assumptions, as well as putting the signals on the cables. In other cases where we have the ability to consider all the ECAD from the PCB and consider representation of the nets on the PCB, we can include that complexity as well. So depending on what we're attempting to do, we can start with simple models and we can evolve them to a more and more detailed full wave simulation of the product.
Okay. What will the role be for measurement and simulation for qualification of devices going forward?
Yeah, that's a great point. So we've already seen this in certain areas of EMC where acceptance of units is starting to be a hybrid approach. So it's not necessarily a question of test versus simulation, or even asking for simulation to replace testing. So by using simulation and testing together, we're identifying problems earlier, and we have an engineering understanding of the EMC performance of our device at a better level than we would with testing. With testing, often it's pass fail. So when we pass, we may not know why we passed. Or if we fail, it sometimes takes a lot of time to do troubleshooting to figure out why we failed. So by augmenting testing with simulation, we can design better products overall. So it's about a harmonious coupling of simulation and testing. So often that does not mean that the programs are going to cost more. On the other hand, simulation can pay its own way because we take less risk in the testing and we have less possibility of retest and redesign. Our simulation plus testing workflow can be less overall cost than doing testing alone. So we have a better understanding of the EMC performance of our product. We're doing it with less risk. And generally, once we get started doing this, we're going to be doing this with less cost. So that's really where this industry is headed. And for many companies, they're already there.
All right. How large of a device can you simulate?
Very large. So today we've focused on electronic enclosures that are relatively small, say a computer desktop and smaller. But in some of our other webinars, we've talked about full aircraft, Navy ships. EMA3D is for devices, but it's also for platforms. And we have the ability to scale to large platforms. So there, it's unlikely that we will hit a platform that couldn't be addressed at least at some frequencies with EMA3D cable.
Is there a limit to the amount of cables that you can simulate?
There's not. So we have had projects where devices, we include every single cable in that device. We've modeled cars and aircraft with every single cable in that aircraft, car, or rocket. So if we have the specifications of those cables, we can get them in the model.
All right, looks like that is the end of our questions. So it is time to conclude this session. As a reminder, any questions that we didn't get to will be addressed via email. You'll also be receiving an email from us with a link to the recording of this presentation. If you have further questions about a particular section, please feel free to reach out through the EMA3D.com website or our email. Thank you for your time and attention and have a great rest of your day.